The existence of aliens had long been the target of astronomers and scientists. They've been doing various research on interstellar space to find some clues on life beyond Earth, with the recent discovery of a massive black object that has been emitting weird signals. Scientists have been receiving these countless signals far away from interstellar space that has made everyone think about the existence of extraterrestrial life. Are we just a step away from finding extraterrestrial life? What have scientists detected? In this video, we'll delve into the specifics of how scientists have recently identified something massive in space that keeps sending us hundreds of signals. Can we ever interpret these communications, or is anyone out there trying to tell us? For many people, the term quick audio burst has no meaning, but for astronomers, scientists, and ardent space enthusiasts, the term fast radio burst, or FRB, is one of the most recent fascinations. Space is full of deep mysteries that may take us a lifetime to solve, and FRB is one of them. Receiving these FRB signals signifies that someone is trying to get our attention. Its mystery stems from the fact that not everything about it has been discovered. When scientists started to pick up multiple FRB signals in a short time, the excitement could not be contained. Should we answer the call? But what exactly is FRB? FRBs are short for powerful bursts of radio radiation that display the recognizable dispersion pattern of radio pulsars. Laura Marenko made the initial FRB discovery and documentation in 2007. The Lorimer burst, also known as the FRB, is one of the most crucial characteristics researchers look at when a telescope detects FRB. However, after pursuing archived data, scientists discovered that the FRB was actually detected about 6 years earlier in a pulsar survey of the Magellanic Cloud. Dispersion is one of the most crucial aspects researchers examine when a telescope records an FRB. Dispersion is just a measure of how to spread out an FRB when a frequency reaches Earth. The plasma present between stars and galaxies causes all light and radio waves to slow down. Lower frequencies experience this impact more strongly and slow down more than higher frequencies. FRBs are composed of a number of frequencies, and the dispersion is caused when the higher frequency light in the burst reaches the Earth before the lower frequencies. The idea is that the more stretched out an object is, the farther it is from Earth. Researchers try to utilize this dispersion to determine how far an object is. Let us quickly describe what the first FRB looked like. It was extremely intense giant pulses from radio pulsars like the Crab observed across a 288 MHz radio band. It was traced to a region close to the location of the small Magellanic Cloud. The instrumentation's narrow dynamic range prevented the scientists from measuring the flux accurately. However, it's been estimated that the FRB occurred in several hundred bursts per day. For many years after the first FRB, with a low possibility of detection presently, it was believed to be singular. One exciting piece of evidence for its existence was that it appeared in 3 of the 13 beams of the park's multi-beam receiver years later. There were other swept sources of radio emissions. Still, they occurred in all beams, and a Swinburne student named Sarah Burks-Palaio published some unsettling findings that she obtained from reanalyzing 2 other pulsar surveys. She was looking for other bursts and discovered almost the exact dispersion of the Lorimer burst. Fast forward to 2013 though, and something dramatic occurred in fast radio bursts, or FRBs. Thornton and Code discovered 4 additional Lorimer bursts when they were given the official name fast radio burst, or FRBs, had dispersion measures that were significantly higher than the original Lorimer burst. The park's 64-meter radio telescope's high-time resolution universe scans led to the discovery of these 4 bursts. The brightest group showed a characteristic dispersion sweep and scatter, broadening with power law dependencies, just as we would anticipate from true alien sources of radio emissions. In contrast, the first FRB identified in another observatory was announced in 2014. However, they have remained disputed with their origins, which is precisely what scientists are trying to figure out because it's so perplexing. It was captured at Arecibo and traced to the galactic's anticenter's direction. Scientists' understanding of the mysteries deepened when they discovered that 1,652 flares were produced in just 47 days after analyzing data collected in 2019. The flares came from FRB 121102's source. which not only broke the record for the most flares ever identified from a nearby, but also gave researchers a fresh perspective on how FRBs may be studied or used to look for periodicity or predictable intervals between similar bursts. However, the absence of any evidence of regularity disappointed the experts. They complained that the absence of periodicity made it challenging to identify the source and pin it down to a spinning compact object, for instance from a highly magnetic dead star or magnetar. However, it was sufficient for the scientists to hypothesize that these FRBs may be formed by more than one mechanism, and they also had to accept that it might take time before the hypothesis is proven. If FRBs represent secret messages, we can even decode them. Apart from the absence of periodicity, most FRB sources only flare once. This makes it difficult to anticipate or trace them. However, a few of the FRBs have consistently sent out signals. One of the most frequent is FRB 121102. It is incredibly active and exhibits a pattern, with 90 days of activity followed by 67 days of silence. Scientists have linked it to a dwarf galaxy 3 billion light-years away because of its recurrence, although it's a real weirdo. The 500-meter aperture spherical radio telescope or FAST telescope that began picking up FRBs allowed astronomers to catch FRB 121102 while emitting one of the instruments that have helped detect the FRBs. Even during its commissioning stage, the system quickly collected the data mentioned above in just 2 months during a 47 period, taking 59.5 hours. The highest level of activity we've ever observed in a quick radio burst, the peak rate was 122 bursts in 1 hour. The researchers classified the bursts in 2 sorts, with greater and lower energy bursts displaying significantly different features, allowing for statistical analysis of the source's activities. The weaker ones turned out to be more random, but researchers haven't given up trying to find them because most other FRBs have periodicity. Those they were able to track were discovered to have come from millions, if not billions of light-years away, galaxies. However, despite their great distance, they create intense bursts that can release the energy equivalent to hundreds of millions of our sun's worth of energy in just a few milliseconds. Using the same FAST telescope in China, researchers recently discovered another FRB designated FRB 190520. This FRB is interesting since it is one of the few repeated bursts and repeats more frequently than the others, producing 75 bursts in just 6 months. The researchers further studied the FRB using the extremely large telescope in New Mexico, and with their help, they could identify its origin. One of the facts was that it came from a dwarf galaxy some 3 billion light-years away from Earth. The team found that of the more 800 FRBs detected so far, only one had a similar persistent radio signal, since they could tell that the FRB originated from a dwarf galaxy. The persistent radio signal was being produced by something from the exact locations as FRB 190520. They were able to calculate the distance between the galaxy and Earth, but the results stopped making sense at one point. To their surprise, their distance estimate based on the dispersion, the FRB, was 30 billion light-years away from Earth, which is actually 10 times greater than the actual 3 billion light-years to the galaxy. This is both normal and unusual. Only 19 of the 800 FRB sources can be traced back to their origins, so the distance from Earth can be calculated for those 19. But for the remaining FRBs, astronomers must only estimate their distance from Earth based on their dispersion. For the other 19 FRBs with known locations, the distances estimated from the dispersion are very similar to the actual distance to their source galaxies. However, this new FRB differs from previous ones since the estimations from the dispersion approach were inaccurate and threw a lot of presumptions out the window. The finding of FRB 190520 brought even more queries that are still unanswered. For instance, the conditions that led to our persistent radio signals becoming more prevalent are the same as those that led to the FRBs responsible for producing the persistent radio signal. The fact that the dispersion is higher than it should be, and that something around the FRB or the FRB itself could have caused it, has puzzled scientists about FRB 190520. The team that discovered the object has committed to continuing to research it with various telescopes all over the world. Perhaps additional FRBs will be discovered in the future, enabling researchers to comprehend them fully. Let us know what you think of FRBs in the comments area below.